everyone, we're Ria, Rahul, and Jason from Columbia University, and our project is titled Cloudy with a Chance of Space Dust. We modeled off of Problem A. Our goal was to understand what happens to tiny pieces of cosmic dust as they fall through Earth's atmosphere. These grains start extremely fast as they fall, and then they slow down, heat up, and sometimes even vaporize completely. What we wanted to know is, if we find these dust grains on Earth today, can we work backwards to figure out what they looked like before they entered the atmosphere?
Our goal was to connect entry conditions to what we actually find on the ground. We modeled the atmosphere as exponential, used quadratic drag and an energy limited ablation law, and solved for two things. One, how fast the particle slows down, and two, how much of its radius it loses. That gives us a survival rule, r prime equals r minus delta r. Finally, we inverted that mapping. We treated it as a matrix equation, ax equals y, to estimate what the entry population must have been.
Cosmic dust might sound small, but it can tell us large-scale things, like how matter travels through the solar system, or like how the paper discussed how even organic molecules reached Earth. The problem is, by the time the dust reached the ground, the atmosphere has already edited it. Some particles survive and some melt while others shrink. So our goal was to mathematically describe how the atmosphere acts like a filter and then see if we can reverse that filter.
We'll start with a few simplifying assumptions. One, every grain is a sphere of radius r and density rho p. That's not true in reality, but it keeps drag and heating easy to calculate, and the results still show the right trends. It enters with speed v naught, and we assume all particles fall straight down so we can focus on the vertical case first. Next, we assume the air gets thinner exponentially as we go up. This is a very standard atmospheric model, as it makes the equation neat and still realistic. The drag and heat transfer coefficients CD and CH stay constant through the hypersonic phase. They normally change with speed and flow, but assuming they're roughly 1 makes the model easier to handle without losing our main behavior. We also assume the only way the particles lose material is through heating, not breaking apart. This process is called energy limited ablation, meaning it takes a fixed amount of energy to melt or vaporize 1 kilogram of stuff. We call that constant Q star. Finally, we ignore lift, fragmentation, and chemistry. Just one body falling cleanly. Each of these keeps the equation solvable while keeping the physics realistic.
All of these choices give us a first-order model, simple enough to solve, but still captures what's really happening.
The first key quantity is called the ballistic coefficient, written as beta, which describes how stubborn a particle is about slowing down. Mathematically, it's the mass divided by drag times area. If beta is small, it slows down early, high up in the air. If beta is big, it keeps its speed deeper into the atmosphere.
So the particle slows as drag grows with air density and the square velocity. Using the drag force and the geometry of descent, we get a differential equation linking velocity to magnitude. Assuming air density falls exponentially with height makes it solvable, yielding an exponential decrease in speed with altitude. High up, thin air causes little slowdown, but near the ground, dense air rapidly decelerates it. Small grains stop high, while large ones punch deeper before drag dominates. As it travels, frictional heating, proportional to air density and the cube of speed, transfers energy to the surface. Mass loss equals that heat flux divided by the heat of ablation cubed, giving dRdh. Faster motion and denser air mean faster erosion. This ties shrinkage directly to local flow, deciding whether it merely scorches or fully vaporizes.
Integrating from top to ground gives us total radius loss. Two parameters control it, beta, the ballistic coefficient, and alpha, how strongly the atmosphere acts. When alpha is large, dense air, or shallow entry, most material burns off. When small, thin air, or steep entry, much more survives. If delta R is greater than R sub zero, it vaporizes. If smaller, it lands intact but reduced. Now we wrap those formulas into a single kernel K of R prime given R, V sub zero, and gamma. It tells us deterministically the final radius for any entry condition. To allow for measurement noise, we make a probabilistic version, a normal distribution centered at R minus delta R for survivors, plus a spike at 0 for vaporized grains. This kernel is the mathematical filter that converts the entry population into the ground population.
If F naught of R, V naught, and gamma is the entry distribution, the ground distribution is shown here. That triple integral literally folds the entry data through the atmosphere's filter. To make life easier, we fix gamma or average narrowly around its mean so we can focus on the size and speed dimension.
To compute this numerically, we discretize. Each entry bin J maps to a ground bin I with probability AI there. Then Y is approximately AX, where Y is what we observe on the ground, and X is the unknown entry distribution. We solve for X non-negative by minimizing AX minus Y squared plus lambda LX squared, a least squares regression minimization problem, where L adds a smoothness penalty. That's a non-negative, mildly regular line, least squares problem, stable and physically meaningful.
Our workflow had 5 steps. One was to pick baseline constants and test sensitivity for C sub D, C sub H, Q sub Q, etc. Two, to choose an initial distribution with bimodal sizes and typical speeds near 11, 16, and 20 kilometers per second. Three was to compute R prime and mark which particles survive. Four was to assemble the matrix A and solve for the inverse problem. And five was survival maps, ground coverage, and recovery distributions. That full loop connects physics, data, and inference.
Now let's talk about the physical constants we used for our model. We used a lot of different experiments and found baseline and ranges for physical quantities based on our assumptions. These values come from standard micrometeoroid entry models. We also did sensitivity tests, meaning we doubled or halved these constants to see how much they affected the outcome, and the baseline story doesn't change.
So let's look at the diagnostics from our run. As for the survival map, nearly all radius and V0 cells survive under the baseline constants, and the discrete grid populates the updated radius R prime in 2 humps, leading to a bimodal ground size distribution. On the inverse, the NNLS with small lambda recovers side and speed marginals plausibly, with no collapse to a single column.
This plot shows where different entry conditions map onto ground sizes. Each point is a ground size band that at least one combination of size and speed connects to. We can see spikes around 1 to 10 microns and near 100 to 1000 microns. These are regions where many entry states converge, meaning the data is informative for inversion. Flat sections at 0 mean no trajectories reach those bins, so ground data there can't tell us anything about the entry population.
In short, this figure tells us which size ranges actually carry information and which are blind spots in the model.
Now let's take a look at the panel data. In the top left panel, the blue histogram shows surface grains clustering near a few tens of microns. Adding environmental retention lowers the overall amount, but keeps the same peaks. The environment changes amplitude, not shape.
The top right shows the recovered entry sizes. They match the true peaks but are slightly smoothed, which is expected when the mapping matrix has gaps.
The bottom left shows the source mix. Comet-heavy inputs mostly stay that way, meaning source type isn't clearly separable by size. The bottom right shows speeds. They're recovered well because delta R is scaled to velocity squared, though some size-speed pairs overlap.
Overall, the atmosphere acts like a size-selective filter. Informative bins boost recovery, and missing coverage can't be fixed without more physics or stronger priors. Like we mentioned earlier, we did sensitivity tests. We experimented with doubling and halving the coefficients. While it was mildly different, the overall shape stayed exactly the same. This means that the qualitative pattern is robust even when the numbers fluctuate.
All of that matches physical intuition. Small grains with low beta break high and survive with modest shrinkage. Faster or shallower entries increase delta R, and a higher Q or steeper gamma reduces it. In simple terms, K formalizes how the atmosphere edits the incoming population into the ground population FG. With mild regularization, the inversion retrieves believable entry distributions.
We've kept the model deliberately minimal. We didn't include fragmentation, sideways motion, or chemical reactions, and those would probably come next. But even with this simple setup, we already see realistic trends for survival versus vaporization. The next step would be to add even more entry angles or separate kernels for different materials like metallic dust versus rocky dust, etc.
So let's talk about the big picture here. The faster a particle goes, the hotter it gets. The smaller the particle is, the sooner it slows down. The combination of drag and ablation explains which grains survive, and the kernel and inversion framework turns sediment data into estimates of what entered from space. In conclusion, by modeling this process, we can connect the dust we find in rocks today to what was falling through space millions of years ago. Thank you. We have also included an appendix with further information and derivations for your convenience.
Thank you.